I'm starting the stream, I think. It's been a couple of weeks. Here we go, though. Hello to Maths2222222. Good to see you. Hello to other people joining. There they are in Twitch on that one. The camera is pointing down. As you can see the t-shirt, though. Oh, t-shirt. Don't miss a chance to tell people about Gaussian Prime's t-shirt. Gaussian Prime's t-shirt. Put the link in chat. There you go. That's how you do a sell. Hello, Me Machine Rex. Good to see you. Sorry about the ads, but good news on the ads front. Hello, Mary, as well. Good to see you. Hope everyone's well. I missed last week because I did a summer school and it made me more tired than I thought it would. I'm getting older, but it was a good summer school to do. I want to show you maybe more than one of the problems that we looked at on the summer school. I can't remember if I've talked about them before, but it feels like a normal thing for me to do is to get back from summer school and then talk about problems from the summer school. It's possible I did exactly this last year and did exactly the same problems. You can tell me. What was I on Thursday? No, it was wow. Anyway, good news. I've got a t-shirt, I'm live, and last week or a couple of weeks ago we talked about Twitch finally hitting a milestone, which meant that Twitch did payout. The payout is supposed to be at some sort of like $50 threshold, which we got to due to all of the ads and occasional subscriptions and things, so well done everyone. Which is a reminder that this stream is supporting the Sutton Trust. That's my chosen charity. We're doing sort of permanent fundraising very, very slowly. Anyway, we got to payout, so it's a number after conversion of currency and possibly some amount of tax. So there's a number that's 2 digits and a bit less than 50, and you can guess what the payout was after currency conversions and rounding down and stuff. Which number between 1 and 50 do you think it would be funniest for my first ever Twitch payout to be? We will see. Yeah, 20 quid would be a good answer, but not. I think missing a punchline. So a larger number than 20. £1 would be also funny after all of the kind of currency conversions and rounding. But no, Twitch is funnier than that. The first payout, they went for £34, which is a number that follows me everywhere. So here we are. At the £34 mark, we got the Twitch payout. Hooray! We did it, chat. They must have analysed the stream to work out the funniest number. For anybody watching this clip out of context, 34 is a number related to a mistake I once made that chat won't let me forget about, and now Twitch won't either. There we go. Thank you. There's a real email from Twitch. RFL, we made it. And I also did the summer school, so we've donated this to charity. We get the on-screen celebration. There it goes. It's so weird to me because it's not on that screen, but it is on that one. I should do something normal over the top. There we go. Good. Donated it to charity, and I'm not going to make a big deal of this, but I felt that everyone had done so much work watching adverts. I know Mary has watched a lot of adverts all. Herb was watching a lot of adverts for the army. Really wanted Herb to join the army. I haven't seen Herb in a while. I sort of worry that Herb has got to join the army. Anyway, I felt that we should round it up a bit. So I did the charity donation, but I put a 0 on the end. So I guess I've matched the donation in some sense. We've donated approximately how much I think is approximately how much I got paid for doing my first ever Sutton Trust summer school, which there's a series of summer schools that I did as a student many years ago now, and doing things like Sutton Trust summer schools. Obviously, they're good for the teenagers on the event, right? They're a chance to go and visit a university and find out about what university is. I'm sure hundreds of people have been to these summer schools over the years, but they're also really good for the students because occasionally the students find out through helping on these things that we actually like doing it and want to do more of it. So that's how I got into doing the kind of maths outreach stuff. Anyway, that's me rounding up the advert, the Twitch ad money. and I think in some sense paying back. One off. I did many of them. So one off the Sutton Trust summer school things. Right, good. Okay, that's it. Let's talk about some maths. What Mean Machine Rex has made a Lego. Oh, I gotta check Discord though. Have I got Discord on my computer? See if we can get it on screen. Oh, I don't know how to log in. No, I do know how to log in. I can do it. For Lego reasons, I will log into Discord. Where do I go? Is it on here? Oh my goodness, it's like an AI Lego character. It's amazing. I love it so much. It's even wearing my jumper. It's this. Oh! They got the hair just right. That does look a lot like this. The jumper piece is what I really want. I want that jumper. Not right now, of course. It's extremely warm today, but that's what I want. It's my two-tone jumper. Thanks, Rex. That looks amazing. That's really funny. Right. I challenge you to find a human who converts to Lego minifigure better than this. Right. Okay. What else is going on? 34. No, that was good. Okay. Right. Maths problem, as promised. Not from a Sutton Trust summer school, but from a related sort of summer school. It's from 2009. It's not a BMO question. Sorry if I've thought about this on the stream before, but I think it's a really good puzzle. It works like this: square root of a plus the square root of b equals square root of 2009. It is a BMO question from 2009. And A and B are positive whole numbers, or maybe 0. Let's go whole numbers. And I think they're allowed to be greater than or equal to 0. Find all possibilities or something. Yeah, solve this. Nice. Oh, you know this one. Brilliant. Okay, have I done it on the stream before? Not that that means I can't do it ever again, but I think it's quite fun. So I'm sort of going to do the people running it. We've been talking about this for quite a lot of time over the summer school, and you know, probably worth talking about. Math 2 is going to come and do something. I can't remember if I did this one. I strongly suspect that I didn't. It's about the right era, but possibly a little bit. I don't think I would have been able to do it as a teenager. Although I think that the structure I've got going is so I had to think quite a lot about how I would help people solve this, and then that didn't actually come up very much in the summer school, but I did thinking. Thinking's good. So to do this question, you will need to know that 2009 is 7 squared times 41, which means that the right-hand side is exactly 7 times root 41, which feels relevant, you know. If these things were both, well, on the right-hand side we've got 7 lots of root 41, and you can kind of come up with ways that these would be something times root 41 as well on the left. You know, if everything is a multiple of root 41, you made that work. Hello, Charlie34711. I missed you coming to chat there. Nice to see you again. Good to see you. BMO question. Maths. Yeah, the root 41 is rubbish. So sort of the tempting thing is to say sort of, what if A is like m squared times 41 and B is n squared times 41? That'd be nice because then the root 41s would cancel. Or maybe m squared and n squared is greedy, but maybe the leftover bit doesn't have to be a square. But what if it's these things like this, and then we get root m plus root n equals 7 or something? That feels more attackable. These numbers aren't very large. Not very large at all. And actually, is this root 3? Not really. I don't like it. Because the root 41s would cancel everywhere. In fact, those are all of the solutions. But that's not really anywhere near a proof of how this works. So this is the right inspiration, which is something I think about quite a lot. So it's the right inspiration, but it's not the right way to prove that this is all of the solutions. Instead, I want to show you what happens if you start just attacking the problem in a way that maybe is I think, most straightforward, which is start squaring things. We've got square roots, we've got whole numbers. I kind of want to square things until I've got whole numbers that, I don't know, add up to 6 or something, and then I could be happy. That'd be nice. It's foreshadowing. So if I square both sides, which is what I like to do when I have a problem involving square roots, here's something like this, which is not too bad. Kind of tempting to take the a and the b onto the right hand side. These terms on the left hand side, send them over there, and square again. But before we do that, let's pause. Matthew is suggesting subtract the square root b instead. I haven't tried that. I don't think I should be allowed to comment on a problem. But you want to do something different. You want to do something different to me. You want to subtract square root b. Are you probably going to square again anyway? Looks like it'll have something better. Ooh, it's interesting to me that you say prettier, because I feel strongly that keeping the a and the b together and treating them symmetrically is treating them the same is prettier. Partly because I want to talk about this inspiration idea. Yeah, so you are going to square. You're going to end up with a cross term that involves 2009b. And a b. And a 2009. And an a. But your cross term is slightly different. Maybe that is good then. Because your cross term only involves 1 and 9. Do I like that? Maybe I like that. Don't know. I'll try it in a second. I'll tell you my strat, which is that the inspiration over here was that we would like to show that both of them are multiples of 41, which in fact is the punchline at the end. It is very much from 2009. We'd like to know that the numbers are both multiples of 41, so we should think over here about the highest common factor. Handwriting. Sorry, it gets worse at the bottom of the screen. A and B. Because of course the highest common factor divides this, and it divides this and this, which means it divides this square root, and it divides this. So the highest common factor divides everything on the left hand side. It divides 2009. It might be 1, it might be 41, or something like that. I suppose my plan is that after I've divided by its highest common factor, I'll have something where a and b, after dividing, I have new numbers there, that don't have any factors in common, and I have a plan for that. Right, pause for anybody who wants to think about that, to think about the highest common factor of a and b, and to see how that reduces the problem down. So maybe a is, let's give it a name, let's call it h, or d or something. D for divisor feels a bit nicer than h. D, so maybe a is dm and b is dn, and we're really hoping that d turns out to be 41. See where that goes. So I suppose then the highest common factor of m and n will have to be 1. Ooh. Because after you've divided by the highest common factor, there isn't any more common factor. So that goes somewhere interesting, I claim. And then I also want to try out Maths222's way. In chat, you say subtract the root b and then square. So that gives this. And you said that shows, and you made it sound immediate. Yeah, this does seem quite convincing. This does seem quite convincing in some sense, because I suppose you're going to tell me now this stuff in here, all of that has to be a whole number. Because it's a whole number. Yeah, there you go. Slightly ahead. Hey, Fanvox fan, good to see you. We're doing a question from a summer school from 2009. Wait, hang on. The question is from 2009, but it was used on a summer school I was on a couple of weeks ago, and that is Math222 in chat has got a better angle of attack than me, which I'm excited about. Yeah. Okay, whole number. Sign patrol, or like plus minus signs. Yeah, we're not too worried. We're not too worried, are we? It's a whole number of some description. Partly a tiny bit worried about this factor of 2, but not really. Not really worried about this factor of 2. In order for this to be even a half integer, then maybe a whole number divided by 2 after I've dealt with this 2 up front. In order for this to be a whole number, as you say, must be the case. Think about prime factorisation in here. B must be a multiple of 41. Got to get these factors up. You want a square number inside here? Where you got 7 squared, that's all right. You have some more 7s if you like. But you've only got 141 in there, so we need to get another 41 from the B. That's very good. Yes. Yes. I shouldn't worry about the factor of 2 too much, you're right. I should worry about it a little bit, but not too much. And then symmetrically, A is also multiple of 41, and then the question just falls over. I like that. Yeah. 41 times a square. Yeah, it is better, isn't it? Yeah. You get the square as well, if you think more. Okay. Yeah, I like that. That's a good attack. This side, what I was getting at with my highest common factor business, which is how I've been cluing this, is that you end up with this. So, because this D has to divide 2009. So then it must be the case over here, M and N are coprime. And let's go for the full points. Root Mn is rational. So M and N are both squares. I think this is one extra step, maybe 2 extra steps compared to the thing on the right. If they're both squares, then great news. One last change of variables, sorry. If they're both squares, then this just becomes u plus v squared on this side. And the thing on the right must be a square. So it must be the case that after dividing by d, you're left with a square number. And 2009 has several factors, but it's only got 2 square factors. So this is a square, it's u plus v squared, it must be square. And the only square factors of 2009 are 1 or 49. If it's 1, then the common factor is 2009, which is quite quickly impossible. Good. Okay, I think I prefer the Maths 2 approach. Just to break the symmetry by subtracting and then go for it. I wonder whether... Do you have... So my impression is, either way, that you need to have found some solutions first. You need to have messed around with it a bit. Well, maybe you just went for it and you started rearranging things and squaring them. Something I've been thinking about is, well, how did you know to look at, the factorizations, to look at what's going on inside 2009? How is that going to be a whole number? Maybe you just got there, but for me, at least, it was trying to work out if I could find any obvious solutions. Right, so messing around first. Okay, good. Phew. Something I find hard about other harder problems is that I can't find any solutions. I don't know what the solutions are going to look like. Oh, yeah, I know this one, Find a function. I think it might be, find a function, because there are many, but find a function from the positive rationals to the positive rationals, such that, and then some hideous looking thing. Just absolutely grievous expression. The function of x f of y. Yuck. F of x over y. It's just the fact that it's not f of y down here is just so like, oh, yuck. I think I did this on a similar summer school last year. Yeah, fair enough. What's the infinite left? Oh, I know, hang on, this sounds like a category theory question. What's an infinite left? Z module or something. So it's not too bad. When you realise that rational numbers, there is a kind of nuts way to write rational numbers that you end up with eventually. Because you're trying to prove this for you start by working out what f of 1 might be, and then you start thinking about f of primes maybe, or thinking about how powers of 2 might work, I think, to try and feed things through. Is that okay? Yeah, so let's try and do some sums. So f stands, write it like that. Maybe not 0. You seem to have banned 0, I can't remember if, yeah, I want to ban 0. You start wondering whether the identity function works, and it does not work. So this one's fun because, it's going to be spoilers if anybody goes on this summer school next year, but how did I do this last year? What did I actually do? Because I can kind of half remember my solution, so I could just try and remember my solution, but I think it's more fun to do the kind of messing around thing, right? Where you try that, look at me, doing questions live on stream, but only ones I've done before. Only ones where I know the answer. So something like setting x equals 1. Well, I suppose just y equals 1 is interesting to me. No, do I just want... So setting x equals 1, y equals 1 is the kind of messing around that you often do with things like this. So f of 1 is f of 1. It's kind of fun. I don't know what f of 1 is, but then f fixes that number. Fair enough. I'm not sure I've ever done an IMO problem. Oh, is this an IMO problem? If so, then I have, and it's this one. Yeah, okay, this might be the only IMO problem I've ever done. Being on a summer school last year and having quite a lot of spare time. It's the only time I got through it. What is this? I kind of remember what I did, but I can't remember how to justify it at all as a thing to try. You know, so you think about prime factorizations again. Why was I doing that? I think because... Who showed me this problem? Oh, I think it was on a question sheet. I think it was on a question sheet from... A question sheet set by a guest speaker at a UKMT summer school that I was helping on last year. I think I remember which one. Charlie, you're doing gap year. You're doing step. No, wait. You've done step 2, right? And you're missing experience. It may have been the same guest speaker. If it was the last question on a problem sheet, designed to keep you busy at the end of the problem sheet. No, what? Charlie, that's really unlucky, sorry. That's the unusual way around. Is it so is that gap year because of that, or is that gap year always the plan? I don't really know. That is rough. Step 2 is often weirder than step 3, I think. Let's do this. What was I doing? Oh, blimey. There's a case study. Take the screenshot. Been having chats with people in Cambridge because the summer school I was on last week was in Cambridge. Not like people. Yeah. So I think the way that the Cambridge system works, there are lots of talented mathematicians who are very suddenly looking for accommodation at insurance options. And that's maybe also partly a fact about how accommodation works at universities as well. 350 a week is insane. Oh, Math 2 is still telling me to put x equals 1 in this. Okay. So this says, I still don't know what f of 1 is. But if I do f twice, then it almost flips this thing upside down to give back, 1 over y. which I suppose means that if I do f 4 times, do I get back? No, not really. Maybe I do. So put in f of 1 over y. Maybe I'll write z to make this feel better. That's my value of y, and then that gives me back z. At this point, I start wondering whether I can just try. I'm only trying to find one of these. That one says I can't set f of 1 be 1. That's a rational going to a rational. At that point, what am I doing? Why did I do this? I was sort of hoping that if I did f twice more or something. What did I do this for? Why did I come in here? That's just rewriting this. What am I doing? I don't know why I write this out with a z in it. Yeah, I was sort of hoping that doing it 4 times would get me back to where I started, which I think might be true, but this is not a good way to prove it. Yeah, if doing it twice gets you back to 1 over that number, then doing it 2 more times should get you back again. Provided f of 1 is 1, otherwise I'm a bit stressed. But let's try f of 1 being the number 1. Is that enough? So at some point I think I started trying to write x and y out as rational numbers, because they're both rational, so you could give them numerators and denominators. I suppose it took me a long time to realise this, but the rationals can be encoded as in a different way. Like this, where m and n and p and q and so on are positive or negative or 0. If you think about a rational number like that, so it's maybe got some 2's upstairs or some 2's downstairs, then you end up with some sort of interesting model. Why do I want to do that? Well, I quite like this idea that you do it twice. If you do it twice, then you're supposed to get to, I'm trying this, you're supposed to get to this. So we've got some operation that we're looking for, which takes this very long vector, infinitely long vector, of prime powers, and if you do it twice, it reflects all of those. It gives you back the opposite vector. So in some sense, I'm looking for an operation that you do it twice and you get a reflection, and that started me thinking about complex rotations. I think because I've seen a transformation where you do it twice and you get a reflection. Multiplication by -1, which would be sort of multiplication by I. And I don't know if this is the thing that Maths 2 got for this problem. We'll compare, I suppose. But at some point I thought it would be fun if my function took the same sort of shape as complex rotation. Yeah, so square root minus the identity, right? But I'm thinking about these as, I guess I'm pairing up the 2's and 3's. And then the 5's and 7's. So I'm pairing my primes together. Let's not use it. Let's use this. Like this, because I know a transformation that on m and n, that if you do it twice gives you -m and -n rotation by 90 degrees. So my plan in the end was to do something like f taking 2 to the m, 3 to the n, 5 to the p, 7 to the q, and so on, 2, and then I want to do a rotation. So instead of mn in the complex plane, I want to go to -nm. And instead of PQ, and the same thing on the next two primes, instead of PQ, I want to go to minus QP, and so on for pairs of primes. Because if you do that twice, so there's a rule there, swap and put a minus on the front one, so then you swap again and you put a minus on it, you'll end up with a minus on both, which does this property. I still need to go and check that it actually does the thing at the top of the question, but I think it does. I need to track the 2s and 3s separately, but I think it all checks out. Let's see. So x equals, it's, I think, sufficient to check this on just the numbers like this. But lots of negative stuff going on. Hey, same solution, nice. Sufficient to check it on these, I think. And then because my function across pairs of primes, it's so for different pairs of primes, it just treats those separately and then multiplies things together. I sort of hope that's fine. I should check that as well, shouldn't I? So if f takes all these 2s and 3s separately, 5s and 7s separately, does its own, does little rotations on them, then it takes x, multiplies all those. You can do that multiplication with the 2s and 3s separately from the 5s and 7s, and then that f on the outside rotates those. That's fine. That rotation is separate on the 2s and 3s and separate on the 5s and 7s. On the right hand side, you can just do the calculation on the 2s and 3s and the 5s and 7s separately. Okay, there's some stuff going on. I think viewed like this, it is just a matrix problem that we're describing on the left, some sort of matrix property where, what do we want? So we want 2m1 n1, and then f of y means 2 to the minus n2, 3 to the m2, because I've done an f to it. And then I'm supposed to do f to this, which, right, gosh, okay, so this thing aside is m1 minus n2. Do you know what? I think that last time I tried this, I was so happy to have thought of this that I did not check it on. Did not check it, which is clumsy of me. So what does my rule say? It says you're supposed to swap the powers and negate the first one. So m2 minus n1, m1 minus n2. And meanwhile, I have f of x is something like 2 to the minus n1. Oh, that's a bad handwriting error there. 3 to the m1 divided by y means divided by 2 to the m2, 3 to the n2. Yeah, Charlie's right. I've missed that thing, sorry. What am I doing with the m1s and m2s? I'm trying to check this on general numbers, but only ones that involve 2s and 3s. So my rule is factorise your number, including numerator and denominator, so these powers could be positive or negative numbers. And my function tells you to look at the 2s and 3s together, and maybe a 0, might be a 0 in there, and to do a kind of little rotation by 90 degrees on that vector of the exponents, which is nuts, but really it just means factorise and then do this rule to the powers of 2s and 3s. So I'm trying it out with some actual numbers x and y with general what are the powers, because I worry that I had this idea looking at this kind of consequential fact in there that we deduced from the top that this expression would hold, but I haven't gone. I'm trying to track it all the way back to the first question, start of the question. Yes. Yeah, so the session is about this. The rest of the session is about realizing that the numbers are an infinite dimensional vector space. So this seems on theme for the rest of the session. If it's the person I'm thinking of, then I first met them when we went on the same summer school as teenagers. I've messed up because this is not the same thing. Possibly, I can't count. Oh no. Yeah, disaster. That's nothing like the right answer. That's good. This is an M for starters. Oh, it's close. It's pretty close actually. It's just this M2 that I'm worried about. And why has that happened? Because I swapped them and I put a minus sign on it. Why did I have a minus sign? because I wrote it out from here and I wrote it down wrong. Hooray! Did go to the same call as me. If it's Richard Freeland, hello Richard Freeland if you're watching. Good, I think we got there because I think this checks out. And this shows that the 2s and 3s are good. I really should try and write out my reasoning for why it treats the 2s and 3s separately from the 5s and the 7s, other than my definition of F, just ignore, just treat certain things separately. And kind of the multiplication is all fine. Yeah, multiplication's fine. This is all right. I'm sort of taking the infinite dimensional space and writing out this matrix. Oh, no one's going to like this. This is the sort of thing that's going to be fun for me to say, but not actually helpful for anybody. Hypothetical vector for the powers. So these are the exponents of the powers of 2, 3, 5, 7, and so on. Take your powers. Those ones. Take your powers, and then multiply that by the following matrix. Oh gosh, what did I say? Swap them and make the M negative. Swap these ones and make the M negative. Swap these ones and make the M negative. Whee! All the way down with 0 everywhere else. Zeros in the matrix. That was fun to say, but not actually very helpful. So then it's on each 2x2 subspace, it's just doing little rotations. Oh, what do I mean? What do I mean? I don't mean vector space then. No, I know what you mean. Do I just mean ring? That's a bit disappointing if I just mean ring. No. Yeah, no, it's worse. I mean module. The whole course on those in uni, and I cannot tell you anything about modules. Oh no, my least favourite sort of thing. That's irritating. Yeah, the integers are not very good, are they? They give you all these nice lattice structures, though. Like the one I'm wearing, right? Although that one's got extra structure from the fact that it's supposed to represent the complex integers. So, more things going on. Good, okay. Those were both quite fun. Anybody else got other problems we should do? I'm just doing random problems. Ages ago, Charlie said something and I missed it. Multiplying the flipped version of the normal one. Ooh, and multiplying them, that would be fun. That would be fun. I did try flipping this over, and then you could multiply. You could also try putting 1 over y straight into this. Charlie has a massive matrix question, which we're gonna be treated to in a minute or so. Yes, please. Was it Charlie who showed me a step question? I've been banging on about Fibonacci numbers, which is something I do quite a lot. And Charlie showed me a step question that was also, I think, that is also what I mean by massive matrix, the infinite sort. Right. What is this? I've worked out Maths 2. It's a senior session. Keep tidying this up. Marvel at this approach for a second. I hate breaking symmetry. I feel like often this is not the right way to go, but then it means you have fewer unknowns inside the square root, so better. Is this the one where... Oh yeah, I've been talking about factors. I think in here somewhere we've got... Yeah, this kind of like this lattice of numbers and factors and things. We put on screen at some point with the multiples of 2 in this direction, the powers of 2 in that direction, the powers of 3 in that direction, the powers of 5 in another direction. Am I supposed to say module for this? Maybe I'm supposed to say module. Time to look up what a module is. In which the field of scale is replaced by a not necessarily commutative ring. Oh yeah, fair enough. Okay, that is what I've got. I've replaced it with my favourite not necessarily commutative ring, which is the commutative ring of the integers. Yes. Oh, and there's the big cat. I need to get this one on a shirt, don't I? This was our successful fractal day, where we understood a thing about fractals. Why is that crossed out? Oh, instead of thinking about states, we think about combinations of states. Ah, this was good. I should go back to this. There's the original cat. Doesn't look much like a cat, does it? The original state, but then somehow the orange one does. Yes, cat. Charlie's going to do it. Go on, Charlie. Massive matrix problem. Find the general solution to this equation. Yeah. Ooh. Okay, Charlie, I'm well up for writing out the first few rows of Pascal's triangle. I'll do that while you tell me the next bit. The idea that there might be even more to know about Pascal's triangle is always interesting to me. I'm trying to learn some other names for Pascal's triangle because there's many. But I keep forgetting them, so I'm going to Google them quickly, put them on my other monitor, and just sort of throw them in. Yankees triangle. There we go. I'm up and running with my alternative names for Pascal's triangle. In Italy, it's called Tartaglia's triangle. You want the top one? Okay. Did I see a YouTube thumbnail that said something like you can extend backwards? Did I see that? Some minus ones maybe? Or complex numbers even? Or just put some absolute nonsense up here? Maybe I saw that as a YouTube thumbnail. Has anybody seen that one? Oh, right, hang on. I've got another instruction. First few rows of Pascal's triangle, and now write a 2x2 matrix, an empty 3x3 matrix. Oh, okay. I do like 1x1 matrices. I tell my first years about 1x1 matrices at one point of a not very convincing rant. My strongly held but kind of fake opinion is that when you learn about derivatives, they should explain to you that this is a 1x1 matrix. It's not really a number, it's a 1x1 matrix. This is my stupid opinion. I don't really believe that, but some things in life make more sense if you believe this to be a 1x1 matrix. This one really, I suppose, the 1x1 matrix that contains that number. Because in higher dimensions it's always a matrix. So in one dimension, for a function that takes one input and gives one output, maybe we should write that as a 1x1 matrix, which would be the same but wearing brackets around the sides. Right, hang on. And Charlie's going to tell me what to put in the matrices. Here we go. If you let the rest of this, you can then derive. Oh no! Don't do x plus. Oh, I see. So you want them to be the coefficients of x plus y and minus. No, I don't like that at all. Do I like that? No. I mean, okay. So I sort of agree there should be some zeros. I do agree there should be some zeros. And this is the sum of these. So this must be the sum of these. We sort of work out, because you could infer. Could you infer backwards? Maybe not. So this should morally be. What do I want this to be? Maybe halves. The sum of. So this one is the sum of two things. I kind of want to keep the symmetry going, so maybe they should both be 1/2. I guess, yeah, okay. Do I like that? Not really, because then there would be a 1/2 here, unless I put minus a halves in. That would be good. Whole row, so I get a symmetrical row up here if it's all halves and minus 1/2. Oh no, because That's not quite true, is it? Because, oh, yeah, alternating, but with 2 in the middle that happen to match. So alternating, but with 2 in the middle. And then I can work it backwards. Oh, sorry, right, okay. Right, matrices. The 2x2 matrix is 1, 1, 1, 2. A matrix that I have seen before. Is this you? Are you telling me about that? No, okay. 1, 1, 1, 2. For the 3x3, put in 1, 1, 1. Okay, here we go. 1, 1, 1. 1, 2, 3. 1, 3, 6. Is that from this table somewhere? Yes, it is. Look, it's this top bit. And then for the 4x4 one, you're going to want me to put, I'll try and, you type it in chat, I'll try and do it on screen while you're going. 1, 1, 1, 1. I bet it's 1, 1, 1, 1. 1, 2, 3, 4. 1, 3, 6, 10. 1, 4, 10, 20. Yes! I'm very satisfied already that I've worked out. Thank you for making me draw Pascal's triangle first. Okay, good. Okay. What question am I going to get asked about these matrices, I wonder? Charlie's typing. They're sort of diamond shaped from the top of Pascal's triangle. So I know a rule for the numbers in each. There's enough information in there. So this kind of is the rule about Pascal's triangle. This is all the stuff you can deduce. First row and column is always ones, and then you can deduce the rest by using Pascal rules. Now say we have the n by n matrix. So I'm going to go dot, dot, dot. I'm going to name them. Ah, you do want the determinant. That's great. Yeah, that's really good. Is it going to be something like the last row? How would I do this by induction? So, ooh, yeah. Not obvious how I would do this by induction, really. Charlie's favourite maths question. Oh my goodness. Right, okay, don't spoil it for me. If I can't remember a lot about determinants, really. What can I remember about determinants? Some stuff about rows, that if you add rows together, will do the difference between 2 rows. That's great. Is there a pattern for the first ones? We're ignoring this first one, I know, but... So 2 take away 1 is still 1. So, suspicious, let's calculate some more. Maybe that one doesn't count though, so we'll ignore it. Over here, oh dear. So doing the determinant the kind of naive way, I suppose, I would go 1 times 12 take away 9 is 3, minus 1 times 6 take away 3 is 3, plus 1 times 3 take away 2 is 1. So that makes me think that the answer is always going to be 1, because it's been 1, 2, or maybe 3 times. I'll do this one just in case. Femvox fan says, is it just 1? What's going on though? So each row, you add, there's a row and a column, but it's kind of not new information when you see this new row, right? Because it's, what is it? Is it the same as the previous? No. So this 10 is 6 plus 4. Interesting. Oh gosh. Am I supposed to remember a formula for determinant? Can I do that? I can probably do that. If push comes to shove, I think I can write down a formula for the determinant, but not a good one. Yeah, okay. I'm now happy it's 1 because I've got two examples where it's 1. Femvox fan says, is it just 1? Just guessing. So they're ahead of this. How's this going to work? I sort of think I might be in for a world of pain if I start writing it down with binomial coefficients though, because what's the hint? Because Well, I don't know many facts about binomial coefficients. That's my concern. I would like to talk vaguely about sums of rows, just for a second. When you add in these extra numbers around the edge, it sort of doesn't feel like new information. So if I subtract the row to the left from that column, that shouldn't change the determinant, right? No, that's the whole point of these row operations. So I subtract this one from that, subtract this column from that column, I'll get 0, which is a good start, 1, 4, 10, which is slightly less of it. 10, 10 again. Now what? Oh, now I'm in trouble. So I think I'm trying to do Gaussian elimination on these. Okay, right. Yeah, okay, current plan I think is Gaussian elimination, do it quite a lot of times. Yeah, keep doing Gaussian elimination, because I can do that on these ones as well. So Gaussian elimination, subtract this column from that one. So this one stays the same, and I subtract it here. So 1, 3, 6, 0, 1, 4, 10, and do it one more time to make this into 1, 1, 1, 1. Keep that one still, and subtract this column from that column to get 1, 2, 3, 0, 1, 3, 6, 0, 1, 4, 10. So now we've cleared out the first row. The first row starts 1 and 3 zeros, doing column transformations. I think that doesn't change the determinant, but it's been a long time since I thought about determinants and linear algebra, because it was formed by repeated addition. So I'm doing repeated subtraction. I've done a bunch here. I'm subtracting like column 2 from column 3, and now what I notice is that down here I've got some stuff that by Fibonacci numbers, I suppose, by Pascal triangle numbers, has the same pattern as the pattern I had before. So I think this is do it again. And if I keep doing this, then I'll end up with a matrix of 1s down the diagonal, probably. So yeah, I kind of want to do it backwards. I hoped that it would be 1 subtraction, just to turn this into like some simple column. But I think the plan is now to just do this kind of repeated subtraction. I could probably build this up into, I guess I know how many subtractions to do to generalize this pattern. It's like n for column n, maybe? Oh, I'm diagonalizing it. I'm diagonalizing it, I realise now, kind of the unconventional way, where I'm going to make it lower left triangular, or whatever it's called. But I'm going to keep going, so keeping the first 3 columns the same. Subtract this one from that one, and you get 1, 4. Subtract the third column from the second column. Subtract the second column from the third column, and you get 1, 3. And then finally, subtract the third column from the fourth column one last time. And now I've got a matrix which is not diagonal, but it's triangular. So the determinant is the product of these ones. Oh, thanks, Charlie. Can I formalize that? So that's my kind of intuition about how I subtract stuff. But I've spotted along the way that all I really did was, in the first kind of round, I subtracted each column from its neighbour, and then I did that again, and I did that again with fewer of them. So something like I'm trying to subtract. No, because I'm subtracting the transformed versions of each one. So what is that then? the thing I'm subtracting the second time is not the original second column, it's a transformed version of the second column. Math22222 says, make the bottom row into 0001. Yes, I would like that. Using a Pascal's triangle formula, yes, I'd like that as well. I was hoping it would just be, first thing I wanted was that it would just be the sum of the previous two rows, which I realise now would be determinant 0, because if it's literally the sum of those two rows, then determinant 0 along the bottom. Once you'd subtract both of those from the bottom one, I guess. My version of this question has Pascal's triangle the other way up or something, and it's a disaster. Yeah, I don't quite know how that would work. Actually, the ones, maybe the ones save me. Yeah, so I've done it with the right-hand side, but I could do it with the bottom row if you prefer, which would then make it upper right diagonal, which might be more helpful. I didn't make it because I did it from the right. I never saw the previous one, so it's not quite induction what I've got going on. Oh, could it be? Is that thing down there the same? No, so I didn't get that matrix. That's a more cunning alternative, isn't it? To try and eliminate all of this stuff, to be left with that matrix. Leave the first 3 rows and columns alone, and try and Gaussian eliminate all of these things. And hope that you get the number 1 down here from doing that Gaussian elimination. Seems clever, doesn't it? So we would need a rule for some combination of these things, which gives us exactly 1, 4, 10, and more generally gives us exactly the binomial coefficient. We know the answer because we know how to do it down here, but maybe we should try and write it out. Oh yeah, and it's really hard over here, isn't it? It's really difficult. It involves ends and involves minus, minus, minus or something, because I'm doing some subtraction of something where I've already subtracted. So you know, like this is column 1, 2, 3, and this is already 4 minus 3, and then this is column 3 minus 2, column 4 minus 3. So when I do the subtraction on the next round, I mean this is then 2 minus 1. Column 2 minus column 1. Column 1 stayed the same in my method. This is column 3 minus 2, this is 4 minus 3. So down here, when I do it again, it's not quite the same thing because I'm subtracting 3 minus 2. So this becomes 4 minus 2, interestingly. No, 4 plus 2, even better. Because it's minus 3 minus... No, wrong. Ah, not quite. Okay, so 4 minus 2 lots of 3 plus 1 lot of 2. Ah, okay. And this, similarly, after a while, becomes 3 minus 2 lots of 2 plus 1 lot of 1. So then when I do the last subtraction on these ones, I'm calculating over here, column 4 minus, so I subtract this thing when I do my last round of subtractions. So it's minus 3 lots of column 3 plus 2 lots of column 2 because, ooh, no, hang on. Plus 3 lots of column 2. Ah, because, right, this is what I mean about the subtraction stuff. I've got column 4 minus twice column 3 plus column 2, circle for column, and subtract the thing to the left means I get minus 3 plus 3 minus column 1, and I claim that's 0 using my knowledge of the binomial coefficients in all of these cases except the last one. So, okay, so my plan to kind of like in a single line like a laser, kind of pew, straight through to the point, and to try and eliminate that 1, 4, 10, I think my claim is for Mn that you can replace replace column n with, and then let's try and generalize this pattern. So that's third. So I've got alternating plus and minus signs, but I want. Is it t-time? It is t-time. What is this then? So this is n minus 1 choose 1. Yeah, trying to generalize this pattern, right? Being a bit cavalier about it. N minus 1 choose 2 times column n minus 2, and so on, plus what's that then? Minus 1 to the k, choose minus 1 to the k, n minus 1 choose k, because I want a -1 on the 1th term, column n minus k, and so on until you get to like plus or minus column 1. And I claim that this gives 1 0 no 0 0 0 1. Maybe I mean row. Let's do it on rows instead. That seems to make people happier. So using proof, using knowledge of binomial coefficients. This looks more like the sort of binomial coefficient facts that I might be able to do. Still not certain. So 2 question marks on the have I got that knowledge in me. So I'm going to do what Mary suggests, which is I'm going to go make a cup of tea, and while the kettle's boiling, I'm going to think about how I'm plugging in binomial coefficients. So I'm writing this kind of shorthand for the column, but I know that the column really is just made of binomial coefficients. So proving this for kind of like the ith element along the row. So like the ith element along the row, my proposal is that we replace that with some complicated combination of what are really just binomial coefficients, and I hope that it just cancels by binomial magic, which would be good because then I get loads of zeros. It does, it's got these plus and minuses. The hockey stick lemma is one of the only ones I know, so let's hope it's that. I'm worried about these. They're both going to be binomial coefficients. There's going to be not just the sum of some binomial coefficients, but the sum of the products of binomial coefficients in a way I haven't quite understood, with plus minus signs in. And the plus and minus signs means it's not just choosing something big. I'm going to write it out so I've got something to have in my mind's eye. The ith element in column I is, okay, so how does this one actually work? You go across and you get rows of Pascal's triangle. Ooh, what are these numbers? You told me to do this ages ago and I didn't take the hint, so I didn't actually write out what the ijth element is. Is it just I choose j? No, it's I plus j. I plus j, choose, doesn't matter, choose I. If this is a matrix, I don't want to write out what it actually is, but the matrix assembly is like I plus j because you look at the diagonals for the stripes of Pascal's triangle. So I plus j, choose, and then it doesn't matter I or j, you get the same number. So in column I, what's j then? As you're working down, so the top row is I plus 0, choose 0, minus, and then I get my n minus 1, choose 1. This is nuts. It's a good question, I like it a lot. n minus 1, oh no, we're starting at the wrong end. Starting at the wrong end, so I'm supposed to start down here. Oh no, column n. Oh my goodness, minus I times, and then this n minus 1th row is, I'm supposed to write here I plus n minus 1, choose n minus 1. Maybe I'm supposed to write 1 and then keep going. Oh no, n minus 1 every time. Starting to regret it being n minus 1, wish it was n, because it's going to be n's everywhere, isn't it? I guess it has to be n's. Not really, but yeah, whatever. Okay, n plus 2th row is going to be this, and it doesn't matter if I write I plus or minus, off you go. And I need to tell you why that is almost always 0 unless I is equal to n. That sounds impossible. Different choices each time on the way down. So I might mess around with some of the choices. Or think about doing some sort of weird binomial expansion thing. No, don't like that. And I might try and check it with some numbers because I've done several levels of hopeful abstraction where I've taken a pattern and I've said, that's probably the thing that always happens, turned it into a big general lemma, which would be enough to solve the problem. But I should probably check it on some numbers to check that both of those leaps of abstraction have actually left me with something that still looks like a true fact. And I'll be, in a minute, holding a cup of tea, probably. I'll be back in a couple of minutes with tea? Question mark? Yeah, with tea. It's a hot day, but I like tea. You know the drill. There's a chance that you will see an ad during this. Ads support charity. Long term, we've just made a charitable donation after a year and a half of doing regular live streams. So it's not instant, but ultimately this stream is raising money for charity. And well, I think I said before, I sneakily did a charity donation at the start so that it would be true, even if we never cashed out. But it's now looking like just a sort of long process. It takes about a year and a half to raise enough money for Twitch to actually bother sending it to me, and then it gets given to charity. Right, good. Okay, I will see you in a couple of minutes. Oh, don't press that button. That is the one that stops it. Press the add button. I'm back, I think. Hello, Mary. Ah, Mary, it's got no ads, which means you, as a reward, you get to look at the screen that says "Be back right soon." But I'm back, and facing us is some hideous claim that for all I and n, claim for all I and for all n, the following thing is almost always 0. We should write that down. 0 unless I equals n when it's 1. This doesn't seem true, does it? No, that's for me, machine raise. Maybe we're not. Maybe, or Charlie. Maybe we're not raising any money for charity. This is great news for the viewing experience, but terrible news for the Sutton Trust, I'm sure. Oh no, Van der Mode is a good shout. I cannot remember what that is, except that it involves loads and loads of binomial coefficients. The only thing I thought in my head, and it's not a clever thought, was that I should expand them all out with factorials. Just go for the definition of these things. That is not clever. Looking at them now, I don't think that's clever at all. Fenvox fan got the ads. There you go. Thank you, Fenvox fan. Oh, the Van der Mode's comment in Twitch chat is devastating to me because I know that whatever I do will not be as clever as. Which one's that? Gosh, yeah, it's absolutely something like this, isn't it? It's that one with all the sum of lots of pairs of binomial coefficients. That's exactly the sort of nonsense we're looking at, with like plus and minus signs though. So I'm still a bit confused. But and also I wanted to be nice, right? I don't know about the 0 or 1 business. Can I get that? Oh my goodness, I do not know. Thank you, crikey. There is a Q analog to this theorem. What a sentence. Maybe I like that. Okay, you know what? Right, good. There is a Q analog to this theorem. Just something you're allowed to say, I guess. Wait, what did that say? 1303. Oh yeah, okay. It was known in 1303. Chinese math edition. Zhu Shishi. Can I learn how to? No, never mind. Okay. Ooh. Good. Right. Okay. Facts, eh? That's what I'm saying. I'm trying to learn other names for Pascal's triangle because I think saying Pascal's triangle makes it sound a bit like a sort of Renaissance thing, whereas it's really not. So this time I'm going to say Yang Hui's triangle, which I think is what I said last time. 13th century. Wikipedia page, which is what I've got on my screen here. The Wikipedia page for this is really nice. It kind of has this diagram and then this one, and I don't know. It sort of feels like you could go to some. You go to different civilizations at different times in history, and they've each discovered, maybe independently or maybe not, but you see the same triangle in lots of places. That seems kind of important. I've been playing a lot of Assassin's Creed, and that's the sort of thing where in Assassin's Creed you'd be like, ooh, ancient knowledge. It's a big thing for those. That's what I tried to say, although I realised that a clever thing for me to do before going live on the internet would be to look up a pronunciation guide. So I realise that now. It was good enough for you to spell it the way I read it, but yeah. That could be my next level of good intentions for the history of mathematics. It's like, actually, you should probably get the names right as well, and maybe don't just have Wikipedia on your second screen. Maybe like actually learn some of this. Oh my goodness. Ah, right, okay. Yeah, Huey was not a good shout, was it? Huey. Right, okay. They're referring to the fact that some websites are going to require ID or age verification, and that's maybe going to include Wikipedia because they lost an appeal. I don't know if that means all of Wikipedia. Maybe it does, which would be bad. Right, how on earth are we going to prove this? Should we try checking it first? It's quite hard to check, isn't it? So let's try and check it on the case we had before. with, and then I suppose I want. Ooh, there's an induction sort of shape to this, isn't there? There's an induction sort of shape to this. Because for the next eye, no, don't be silly. No, okay. Yeah, so I think the idea is that Wikipedia contains, maybe just hypothetically, but contains at least one page that could be read by a child, and then they would get. It's not. I don't know. I don't know if there's a list of like specific pages on Wikipedia that the government would not like children to see, but it possibly means that all of Wikipedia might be hidden behind an age gate, which seems daft. But hey, I can never really tell. There's so many memes and sort of fake news around this online safety bill thing that I have absolutely no idea because I haven't been paying that much attention. Right, so possibly I'm spreading fake news. Sorry, please fact check me on the maths as well. That's probably a good idea. Let's put some numbers into this. I like I equals 3 and n equals 4 because I think that's one of the hardest cases we had just now. And I already see that this is interesting because this is talking about 7 choose 4, which I don't remember coming up in my life so far. The largest number I can see over here is 20, and that is 6 choose something, so I'm already suspicious that I've messed up. What do I want? This one here, column 4. Is there a -1 that I've missed? Yeah, there is a -1 that I've missed. See, this is how you find -1s. You just sort of stub your toes on them, don't you? That 10 down there. Oh no, this is 20. It's the largest thing. It's in space 4, 4. But it's actually merely 6 choose 3. So I'm out by 1. Or maybe I need to be 0 indexed. If I want that to be zeros. Oh gosh, okay, so devastatingly effective checking my working out. This is wrong because in the 4, 4 position down here, maybe they're 0 indexed. If my matrix is 0 indexed, then I think I'm okay. Yeah, let's just say that. Let's see if I can get away with that for a bit. I don't think I'm going to enjoy this. Counting from 0. So the top left thing is 0 choose 0, and then this is 0 choose. This is 1 choose 0, 2 choose 0, 3 choose 0. Nice, 3 choose 0. That should be 1 choose 1, shouldn't it? Oh, I don't know. I don't know anymore. I only want to subtract 1. Okay, let's just try and do it properly. No more counting from 0. I'm supposed to subtract 1 from both of these, I think. Some sort of out by 1 stuff. Oh, Charlie was trying to tell me about this before. Sorry. So, where were you hinting at? Can I scroll up? Oh, do you just mean ages ago when you told me to try writing out binomial coefficients? And now maybe you're trying to save it. Yeah, you said consider binomial coefficient. You didn't know at that point that I was going to get it wrong. So 1 plus 1 is 2, minus 1 is 1, 1 minus 1 is 0. Yeah, that's good. So then this means zeros. Oh, I could have got a duck. Oh, I heard that there were ducks in the goodie bags from someone else who was helping on the summer school. A new innovation that they just give you a duck. So that's good. The ducks are kind of taking over. Did they start any? So the ducks are kind of a running joke from a previous year. Do you think that this year, this summer school started any good new running jokes? Last year, one of the ones I was on had a good attempt at getting the phrase "circles aren't real" to try and catch on as a sort of running joke. Rubber duck, I think. I wasn't there, but I hope it's rubber duck. Yes, it's a sort of it's a UKMT summer school, I think. Right? I'm trying not to out people's locations, but I guess you're not there anymore. I think you've been on a UKMT summer school, which is something I helped on last year, and they're very keen on ducks. There you go. Lots of things. Some duck impressions. Right, out for a duck. So cricket. Oh, there we go. Everyone's got so great. Yes. Okay. Brilliant. Well done, everyone. Right. So I've got to put my binomial coefficients, and I now realise I've got them wrong. So I'm going to subtract 1 here and here, and then deep breath here and here, and here, and interestingly here. Still I. Maybe I should have written I every time because I was just in that. The ith element in column I. So this is not really the ith element because I'm counting from 0 here as well. 0 indexing is going to get me everywhere, isn't it? It's going to get me so many times. So in column I we have, let's just write that. Let's forget we ever said ith element. And just say in column I we have, and that was what the sentence should have been. And I could be 1. This is going to kill me. I could be 1 to n minus 1. I should write this out as well, shouldn't I? And then I such that I is between, for all I less than n minus 1, or I suppose it equals to n. Why not knock yourself out unless I equals n? It's almost always 0 unless I equals n. Good, okay. Hi, Sensation Black, if I hadn't seen you already. Good to see you. Welcome to Twitch chat. You missed about an hour ago the funniest possible Twitch payout, which is that Twitch, for the first time, sent me some money from all those ads you've been watching. The net payout was about £34, which is a funny number. We gave it to charity, and then we did some maths. I sort of not saw it coming because that would be nuts. I'd have to do currency conversions and stuff, but I knew it was going to be a number at most 50, and I sort of wondered whether it would be a number that everyone seems to like. Right, okay, so 20. So I'm trying to recreate this calculation I did over there. Still not happy because this 20 is what it would be. Oh, do I want to out by 1 all of these i's as well? Oh yeah, I minus 1. Out by 1 all these i's. Yeah, I'm supposed to have I minus 1 down here. Let's just go I minus 1 everywhere. Okay, third time lucky. For example, with I equals 3 and n equals 4, I think I'm trying to work out the third thing in that fourth column, the thing where I had tens, and it turned out to be 0 after loads of work. Calculating this sum, we got this 0 here. So I'm trying to check that my generalization works for that. Here we go. So the suggestion is that it's this, and then 5 choose, so it's referring to a different row or column or whatever, it's symmetric, so who cares, but different row or column or something, plus, and then this will be 3 choose 2, and this is 5 choose 2 again, and then minus 3 choose 3 is 1, 5 choose 1. Am I supposed to go? I feel like I have an out by 1 error now. Not 5. This goes down. 6, 5, this is 4, this is 3. Choose 2. And then I feel like I'm supposed to have another one. This hasn't quite worked. This is column 4 minus column 3 plus a lot of column 2 minus a lot of column 1. I feel like the column 1 thing should have gone down by now. That, don't tell me, that 10 is actually supposed to be from 5 choose 2. So I'm still out by 1. Still out by 1. Oh, this is from Timothy Gowers. Ah, cool. Timothy Gowers taught me at university a little bit. In my first year, I had some small group supervisions with Tim Gowers. It was a bit scary because he's Tim Gowers. This now reconfigures in my mind how anything goes now. Me struggling to get out by 1 errors to go away is exactly where I was at in first year university, and Tim Gowers being Tim Gowers and making some sort of bigger point. Why are you scrabbling around with all these -1s when you could be, I don't know, hit it with some theorem or something, was my impression. No, because he'd have been doing it properly. Is this from his YouTube series? Oh, am I copying Tim Gowers' content by mistake? Oh, no. So I was aware Tim Gowers has started doing videos again. I haven't seen them yet. Is this it? Oh, no. That just made me feel bad. I still feel like I had a good half an hour of having ideas and basically working out what's going on, and then a terrible half an hour of trying to formalise it and being out by 1 on everything. That's like 3 years. Oh, I'm really behind on Tim Gowers' content. Maybe that's me. I can do some sort of big picture thing, but then actually trying to work out all the details and being out by 1. Maybe it's my format. My format also doesn't give me very much writing space, which I've blamed before a lot. This moment is where I feel like I was emotionally done with the problem, where we managed to get everything to cancel and it just cancelled. And checking that it always does that. We discovered a secret of some binomial coefficients and alternating plus and minus signs. Still haven't made it work because I'm still out by 1. Right, okay, let's have one more go at calculating that number. And it's a chance to refine our statement as well, because I'm still out by 1 on what I'm actually claiming about binomial coefficients. And I don't want to be out by 1, I want to get it. Because at the moment we have this 6 choose 2 number is 6 choose 2 is 21. And then that's 15. So I'm doing some sort of statement about 6 choose 2 is 15. And now I've got some, I don't want 6 choose 2 at all. I don't want anything about 15s. Not until the next fact. Yes, I'm out by 1 in that direction. I've been telling you about 15 when I wanted to tell you about 10. It's quite bad, so I need to come up by 1. So I'm still wrong, right? Because I'm currently trying to tell you that 3, 4 is not 6 choose 2 at all. Or 6 choose 3. It's kind of worrying that those are different, actually. It is 5. So 4, 3 means I'm supposed to subtract 2 here, doesn't it? I plus j minus 2, because this is the second thing here, and it's where I plus j is 3. No, wait, I plus j is 1 plus 2 is 3. 1 plus 3 is where it's 4, so I need to subtract 2 from this number. But you can keep that thing down there. And then you could write j minus 1 here, and that would be fine. That's the symmetry property. So that's symmetric. And just to check, if I put in 4, 3, then I get 5, I get 2, which is that 10 down there. So it's fine. I was just out by 2. I sort of wonder whether fixing my out by 1 or indexing issue would have just been a cleverer way to say this. But here we are. So what am I actually claiming then? I think I'm trying to subtract another 1 from these. And also there's this annoying property that I'm talking about different rows of the matrix, so I have to keep subtracting 1 to talk about, that's my coefficient in the last column, which is where I start, but then I'm doing all these transformations to it by subtracting other rows. So I'm supposed to subtract 3 or 4 and keep going, I think, to keep talking about I minus 1, the same column of this final row, but now maybe I've got to the point where I've got a true fact that we can investigate, I think. And then our last step, and it'll be worth it, I think. Hello, Famished Edits, how are you doing? I'm good. I've just seen your chat message, sorry. So we're going to check that this is true. And then we're going to try and prove it. That's the fun bit. 3 times 3. So this is the calculation that I did a couple of times earlier, but now written out in a nice compact format, which gives, it's not going to be 0, is it? 5 choose 2. I've rushed that. Oh, I shouldn't have rushed it because now I'm going to have to fix it. It's been 10 all along. That's been the whole point that we've been trying to get 10 there. 4 choose 2. Could be 6. Could be 6. Oh dear, I've come all this way and I'm going to be thrown apart by multiplication errors. Minus 18 plus 9 is the same thing as subtracting 9, so I get 1, take away 1 really is 0. Okay, so that's the pattern I would like to try and generalise. I might try and write it out again. Possibly not using I and N. The thing I think I've got here is you can choose any number here and here, and then you're supposed to subtract 1, subtract 1, subtract 1, but do this alternating. What's going on there? So I'm going to keep subtracting 1 from the top number until I get down to so the pattern is it subtracts 1 along here until you get down to this one, which is 1 at the end, because you're going to hit that small number at some point. However many terms you've got, you put those binomial coefficients in with alternating signs, and the result is that you always get 0, unless I was equal to n. What would I equal n equals n mean? There's some case where you don't, which involves loads of these terms. N of them, where n is I is equal to n, then if I was equal to n, then this top number is twice as large as the bottom one. There's some special case where not 5 choose 2, but the next one 6 choose 2. So let's do that pattern. Let's do the smaller one. So smaller pattern, I claim that if I do this and then interleave it with 2 choose 0, 1 choose 1, 2 choose 0, 2 choose 1, sorry, 2 choose 1 and 2 choose 2, and interleave it with some minus and plus signs, then I'm supposed to get 0. It does feel very much like, you know, if they're equal, then you get 1, otherwise it's 0, and there's some sort of, I've seen a few binomial facts with plus and minus signs in. Maybe I've only seen one of those really, but here we go. So 4 times 3 divided by 2. I'm still struggling to work out 4 choose 2, which is quite embarrassing. So that really is 1. So I want 1? Don't know. I suppose that's twice as much as the number below. So that's my rule, I think. If you're exactly on the middle, I suppose without more generality, choose any binomial coefficient, you can run this process. First, choose that to be less than or equal to half of the number at the top, which you can always do. You can flip it to the other side of the triangle, somewhere on the left. Somewhere on the left of the triangle, you'd have this binomial coefficient. Subtract down like this. Put in your binomial coefficients for how many terms you've got with plus and minus signs, and you get 0 unless you're on the middle, in which case you get 1. Mad. A couple more examples. 6, 3. So 6, 3, 5, 3, 4, 3, 3, 3. That's a double one, so I've got 4 terms. So I'm going to write out 3, 0, 3, 1, 3, 2, 3, 3. And then I'm going to put in plus and minus signs. And I'm expecting to get 1. So 6 choose 3. 6 choose 3 is 20. Because 5 choose 2 is 10, and you add them. So quite a lot of numbers here. 5 choose 3 is 10. 4 choose 3 is 4. 3 choose 3 is 1. Minus 3 times that plus 3 times that minus 1 times that gives me 60. Take away 30. Take away 12. Oh, it's nowhere near. Miles off. Good. Why has this one failed? Which number have I got wrong? It's probably one of them. No, these are the choose 3 numbers, aren't they? 1, 4, 10, 20. It's that 3 at the front. 3 choose 0 is 1. So 20 take away 30 is minus 10, and plus 12 is 2, take away 1 is 1. But 6 choose 2, if I start there, then I get more terms. So that's a confusing choice. So I need to put in 4 choose 0. trying to work out the pattern a little bit here. Minus, plus, minus, plus. Which identity is this going to be? And then triangle numbers 1, 3. So triangle numbers 1, 3, 6, 10, 15. 1 take away 4 times plus 4, choose 2 is 6. Take away 4, choose that, plus 1 times that. Minus, so 15 take away 40 is minus 25, plus 36 is famously 9-ish? No? Why did I try and do maths fast? 15 take away 40 is minus 25, plus 36 is 11, confusingly. 11 take away 12 is minus 1, plus 1 is 0. Okay, so I think this is, if it's twice the number at the top, then you get 1, otherwise you get 0. I am trying to speed up. Right, so what on earth is this fact then? There's two numbers. So there's two numbers. We have. I'm going to rewrite it with the different numbers in here. So I don't think these are going to be the same as my I's and J's I had before. I don't even like I because you have to write too much stuff like K and N plus K. Nope, don't like K either. So what do I think is going on here? That sounds like a clue. They work nicely in matrices to give determinant 1. Yeah, what does that mean? Coefficients, right? Coefficients of... No. How'd you get these coefficients? So the 4 choose 0, 1, 2, 3, 4. So the thing I would like is a nice reason why that's 0. Because then probably my nice reason generalizes. So the 4 choose something coefficients remind me of course, 1 plus x to the 4. The different coefficients that you get. But then they've been multiplied with something else. So I'm wondering whether I can multiply that polynomial with something else which has coefficients, triangle numbers, which seems a bit unlikely. Seems a bit unlikely. Coefficients, triangle numbers. And then this would be with minus signs as well. So what do I think? 1 minus x to the power of 4. So 1 minus x to the power of 4 gives this pattern of 4 choose 0 minus 4 choose 1 plus 4 choose 2 with different powers of x. But the way you sum coefficients like this is you multiply by some other coefficient and you polynomial and you ask for the coefficient, which you can maybe do using knowledge of polynomials. What's it been multiplied by? So I've been thinking this is like the triangle numbers read backwards. So is there a formula for this? The plan is that I sort of take this polynomial and this one, 1 minus 4x plus 6x squared minus 4x cubed plus x to the 4. And then this number that we're looking at is the coefficient of something. Coefficient of... Oh, have I got them kind of in increasing powers in both directions? That's fine. First one's symmetric. Even numbers, whatever. We'll fix it in post. I want... it's the coefficient of x to the 4, isn't it? Because the coefficient of x to the 4, when you multiply those things out, will give you minus 4 times 3 plus 6 times 10. No, 6 times 6 minus 4 times 10. So if I had a formula for this polynomial, if I had a formula for that polynomial, which escapes me, annoyingly. But if I had a formula for that polynomial, and I know this one, then the question becomes, when you multiply these, why is the coefficient of x to the 4 0? Which depends on the formula, but you could differentiate it a lot of times, couldn't you? Don't know how to do that. Yeah, so 1 minus x to the power of 4 gives you this polynomial down here. And which is how I've seen, by the way, before. So this polynomial, if you plug in the number 1, that's a nice proof that, okay, forgetting the triangle numbers in here for a moment, you get 0 because you've expanded out 0 to the power of 4 if you put in x equals 1, but you get confusing 1 minus 4 plus 6 minus 4 plus 1, so it looks like a confusing fact, but really it's just 1 minus 1 to the power of 4. That's something I've seen before. I'm considering multiplying that polynomial by some other horrible mess and then trying to argue that you still get 0 when you plug in 1. Yeah, I don't want to quite plug in 1, I want the coefficient of x to the 4. So that's a bit irritating. Maybe this isn't a helpful thing to think. Is it the right shape for Van der Monde's identity? Let's have a look. Van der Monde's identity down here, our fact up there. No, it's not, is it? In Van der Monde, the things at the top stay the same. They're all added. In ours, the things, excuse me, change along the way. Rats. So we're increasing downstairs and decreasing upstairs. Excuse me? The values of the different sums. So there's sometimes 0, sometimes 1. Huh, okay, so I'm stuck on the annoying bit of actually trying to... Oh, the things I've calculated, this thing is, oh sorry, 0, it's just off screen. I set that up wrong. The edge of my screen is now the edge of your screen. So this thing's 0. It's almost always 0, unless, for me, this starting point has twice the number of upstairs and downstairs. Which is the case here and here, but not here. 5, choose 2 as the starting point. Why does this always work? Have I just backed myself into a dead end? So this is my kind of key idea, is a way to calculate this 6 choose 2 thing, but not the 6 choose 3 in the final row. I'd also like to know why it's precisely 1 when you get 6 choose 3. But if I could do that, then this is the right kind of subtraction of all the previous rows. This is what you would get, and I need to argue that this clears out the last row except for the final number, which puts it in a perfect position to talk about the determinants, which was the question. Okay, so 6 choose 4. Yeah, what does happen in that case? My kind of feeling is that 6 choose 4, you're quote unquote supposed to, don't be completely wrong, you're sort of supposed to flip that round to a 6 choose 2, but let's do it like this. Does this work? So I'm going to write it out. I mean, this minus twice this plus that. But then to calculate them, I'll remember that 6 choose 4 is 15, 5 choose 4 is 5, and 4 choose 4 is 1. Because this actually fails in a different way, but it doesn't give us 1 or 0, right? Is 6 choose 4, 6 choose 2, 6 times 5 divided by 2 is 15. So that fails in an interesting way. Oh, but it is 4 choose 2. I mean, that's true. Lots of numbers there. Yeah, I suppose I'm expecting the cancellation to sort of... Oh, you might hope that you're hoping for a more general right-hand side. Oh, nice. Okay. So some sort of more general right-hand side which includes things like that, which don't give 0 or 1. That's all more ambitious, right? So going for the bigger fact. I like that. I only need the ones that give 0 and 1, but maybe there's a bigger pattern going on. Right, I've got 10 minutes. Let's see if I can get any of this done in 10 minutes. I'm running out of ideas. Might try factorials everywhere. It's not going to be pretty at all. It's not going to be pretty at all, is it? Because the increasing decreasing pattern is pretty horrible. If they were both increasing, then you would have like constant terms, but it's quite warm. Also hard to generalise. You're going to give me hints next week. Cool. What am I doing? I feel like the polynomial thing was the closest I've got to a good idea for how to sum things like this. I suppose, going back to what we said about intuition, I should probably return to my like mood board thing, which is after doing, maybe I could do this better claim that after doing just one subtraction, I spotted along the way that I had not just any old matrix, but I had the same thing translated down by one. That's got to be easier, right? That's obviously easier as a thing to do. Yeah, so maybe I should just structure it. Instead of trying to prove this audacious thing down here, maybe I should just come up with a reason why it does this. I think this is good enough. Ha. And I'm open to the idea that this could be wrapped up into some complicated expression like the one in Twitch chat. But maybe my proof should be something more like, well, what am I actually doing in this first round of subtraction? It's kind of obvious that the ones along the top are going to cancel to give zeros, and then underneath you've got things like I plus j minus 2, I minus 1, for let's say this 3 here. And I'm proposing to subtract the thing to its left, which is I plus j minus 1 minus I minus 2. And now let's get stuck in, because that is a binomial coefficient fact, which we can say is, right, I can do this. How do binomial coefficients actually work? What's the correct right-hand side here? It's something like I plus j minus 1, choose something, and now I'm going to think a lot about what that thing is. Right, how do these work? So it's, no, or maybe not I plus j minus 1, maybe I plus j minus 2. I have a mnemonic for this, which I'm going to try and work out. So I do know how binomial coefficients work, I promise, but I have a mnemonic for it, which is if you're trying to choose this many from that many, then you have all the ways where you choose this many. You label one of them objects as special, and this is the ways where you include the special object. So you choose among fewer things. Among fewer things. Oh no. Oh, okay, interesting. I'm subtracting the thing on its left. It's a smaller number, yeah? No. The thing on its left is I minus 1, so it should be minus 3 here. There we go, good. So you can choose from a smaller number of things, you can choose a smaller team, or from this many things, you can choose a smaller team or something. Those are the, no. You can choose the correct size team. So if you're trying to make a football team, you can choose all of your players ignoring, no, still out, still out. From a smaller team, or from what on earth am I doing? Tim Gowers has done a video on this if you want to see somebody actually doing it. That'd be for some reason I'm doing it live on Twitch. Oh gosh, how do binomial coefficients work? Is this true? If I got there? From I plus j minus 3 from the other ones, not your star player, you can choose I-2 and put your star player on, or you can choose I-1 of them and not run your star player. And those are the possibilities. These things are 3 hours long. You can watch 3 hours of Tim Gowers doing this with more success. And this is what I want though, because that is the number above. So after doing this subtraction of columns, I'm left with the thing which I would have got if I just read one row up, j minus 1. So the number above. So that's kind of a proof. I haven't quite labelled it or put any words on screen, but it's kind of a proof that when I do this round of subtractions, subtracting each column from the one to its right, that I get down here in the box, I get the same matrix shifted down by one row. So here, this 3 that I get out, okay, so maybe point the arrow somewhere else, If I point this 6 down here, I do 6 minus 3 and I get 3, but it's the 3 that was above. If I do 10 minus 4, I get 6, which was the number above. And that's this general rule about what's going on, based on my rule for what the coefficients are when you do the subtraction leftwards. Subtraction leftwards gives you the other number, because in each case, let's do a picture instead. In each case, the number in Pascal's triangle, was the sum of these two things. So when I subtract the rows, I will get this thing. So if I subtract the 6 from the 10, I'll get 4, because 10 is, by Pascal's triangle rules, made of 6 and 4. Yank away. Good. Okay, thanks, Barry. I was worried. Okay, so you get the thing above. Do it again. So if you keep doing this, why can't you do this on the left column? There's nothing to subtract from it, so you're stuck with the 1 at the top there. So just keep doing it, and this will always happen. It always just shifts down, at which point we can just do it again. This matrix, okay, fine, relabel it, cut the corners off, but this matrix is the top. No, not quite the top. It's the top right stuff. Top right stuff, and then this matrix down here, after you've done it again, 1, 1, 3, 4, is the top right bit of here. But the same rules apply. It's a special case of the Q Vandermonde identity. Okay, fine, I'll click on the Q Vandermonde identity that we hovered the mouse on. Oh my goodness. What's the Q subscript? As is typical for Q analogues. Oh gosh. Oh no. Oh dear. Oh dear. Using this Q binomial coefficient, the Q Vandermonde conversion like this. What on earth is going on? What are these? Oh my goodness. Like this is a polynomial. Fun. Oh my goodness. Not sure how much it helps. There are some polynomials in here. There's some things that might be useful. Hello, Super Snowman. Good to see you. Sort of celebration stream. We're doing some random problems because we hit a streaming goal, which is good. Not that one. We're still going on that one. But we finally seen enough adverts that we get to actually support charity, which is something that I've been saying for a couple of years. So celebration stream, we've done problems that I've seen before and a problem that I hadn't, but I feel like, yeah, okay, I've decided that building this iterative process that I'm describing, that building it up into this kind of observation that doing this iterative subtraction stuff gives you a version of Pascal's triangle, that building it up into some sort of fact is not actually helpful. I should go for it. I was already done over here, I think, emotionally, and now I think also mathematically. But this is the correct algorithm for columns of subtraction. Do I want to try and prove this, or do I want to try and prove the Maths 2 version? A little bit. And now it's reminding me of something where yeah, so I think I should try and make this thing more precise. So the way you would prove this then Okay, let's try and prove this. Why did I say that? I've got 5 minutes on the clock. The way you could prove this, I think, is to split the big binomial coefficients apart into two smaller cases, and because it's an iterative plan, so try and unpack the last step of that. I actually made this by doing lots of nested subtraction. I did, so given some numbers like A, B, C, D, I did A minus B, B minus C, C minus D, and then I did the differences again, right? So this gives you 2B plus C, B minus 2C plus D, and then down here, A minus 3B minus plus 3C minus D for the sort of differences. But that means that if you want to understand where that came from, then really you need to look at this 3. So I suppose I should look at these coefficients and split those apart. To understand this any fact at all about this, I should understand it by going back to understand that this 3 came from a 2 minus 2 and subtracting a 1, right? So subtracting 3 here is because I was subtracting 2 and I was subtracting 1 for kind of different reasons. So maybe I should pull those apart and say the kind of coefficients on here are kind of a coincidence from all this kind of combined subtraction that I'm doing. And really, if you unpack this, then it's the difference of two things. So I've got these 4 terms on here. And of course the ones on the ends are not so bad. So strategy to simplify this thing down here. So to simplify this, instead of calculating all of the terms, something I could do is take that 4 choose 1 and write it as 3 choose 0 plus 3 choose 1. Is that true? Is it that way around? Yeah, 3 choose 0 plus 3 choose 1. So I could write it as 3 choose 0 is actually the same thing as 4 choose 0. So I'm going to just do that switch for 3. So to break it down to where it came from. So this is this minus also 3 choose 1 of these. But to use that 4 choose 1 is made of these. Where did it come from? And then that 4 choose 2, where did that come from? That came from 3 choose 1 and 3 choose 2. Have I stacked these incorrectly? I think I've stacked them incorrectly. I think I want them this way around. 1 0 2 1. Stack them this way around. So what's my next thing down? 6 5. This was actually a 4 choose 2 I was talking about just over here. The first one is a coefficient. The second one is an actual number from the problem. And there's 4 choose 3. Where did that come from? Well, it came from a 3 choose 3 and a 3 choose 2. 3 choose 2, 3 choose 2. And then this 4 choose 4, where did that come from? Well, that's the same thing as 3 choose 3, so I'm just going to write it over here. So then I've taken my kind of decreasing sequence of, what have I got now? I've now got something with 3's in instead of 4's in. Don't love it. Don't quite love it. So this thing down here, that is precisely my 5 choose 2 fact. So by induction, I know a fact about this. So that's pretty good. I'm a bit nervous because I don't know a fact about this one up here. I think it's missing a term. No, what do I think? It's got 3's in instead. It's horrible. That's a shame. I was hoping that this would give me some sort of relatable fact. You know, relate these previous things together. Thinking about my A minus. So if you want to know where this comes from, you have to think about how that A on the front is always A. It came from this. It came from this difference of these things. Difference of these things? Yeah, difference of these things. And where did they come from? Well, they're also differences. So I guess this is going to boil down. I could also split these. You could sort of split it back down into the kind of atomic parts that you had, where you got it from. Oh, don't say inclusion and exclusion because it's probably just that, isn't it? Every time Maths 222 says a thing. Right, might come back in 7 days. We'll see. But I sort of my new strat I think is just to unpack it and use some sort of induction, possibly on a slightly stronger form of a statement. possibly something slightly stronger, if I have an opinion about what these things are that we have along the way, and I kind of do, because my opinion kind of is that after doing several rounds of subtraction, you have matrix shifted down a bit. So they should be binomial coefficients, which is something that Maths222 said in chat at one point. They tried different values of the sum, we got 6. I think because in my head we haven't done enough subtraction yet, maybe? Good question. Thank you, Charlie, for proposing it. You would like some advice, so I'll hang around for a second. I'm also going to use this time to plug the t-shirt. Why not? T-shirt's also raising money for charity, but it's slightly a faster rate. But you know, if you like the t-shirt, which has got Gaussian primes on it, there's a link in chat. That's right. I now have merch. I'm very pleased with myself. It's also available on a mug. Have we got a thing for that? What have I seen at UKMT? I've seen notebooks, I've seen biros, I think I got a tote bag once. Oh, I've still got it. Chucked it in the corner and it's still there. That's the thing about mess, it just sort of stays there. I've got a tote bag from the UKMT. They're pretty good. Lots of merch. Charlie, a suggestion. So you've already done a lot of step, which is something I sometimes suggest that people do. I think it is quite tough. You said earlier that you were going to do some IMO problems, which sounds really hard. Something I've found quite helpful for keeping my hand in maths is to just have some problems bouncing around. I quite like this one, so it's probably going to bounce around in my head. I found it quite hard to keep doing maths while also doing something else. I have a job now, so I only think about maths in like, I think about this or maths separately. So I think anything that keeps your brain turning over and trying to solve problems is probably good. You have this kind of danger, I think, possibly during your gap year, that step becomes too easy, but it sounds like you're fighting that by also looking at IMO problems. I'm not sure that step really can become too easy, and if it does, then you've become really good at that sort of maths. So kind of a good thing to happen, I suppose. But in some sense, anything weird. We've been thinking about quadratic forms on this stream, so I'm going to finish by giving everyone a question. I've changed office, so I have an office problem. So my office number was a triangle number. I added a square number. So triangle number is n plus 1 over 2. I added a square number to it. My new office number is, wait for it, is a centered hexagonal number. Let's write that up. Centered hexagonal number. Can you find some possibilities for... it doesn't quite work as a puzzle because there's lots of solutions. So maybe this needs to say they're all 2-digit numbers. I'm not sure it's a good puzzle. Sorry to attack my own problem before I've even finished saying it. But I think I haven't quite worked out how to give you enough information that you can work out the numbers, right? So they're all 2-digit numbers. Is that enough? In order to set this problem, I would quite like to know all solutions. And I think I've got close to finding all solutions, but I'm not sure I'm there. So this for me at least, this is open or interesting to think about of how many of these are there. So examples of centered hexagonal numbers are sort of 1, 7, 19, 37. They're ones like this. So 7, like a nice hexagonal grid with a kind of side length. This one's got side length 2 around the outside. It's a centered hexagonal number. And these ones are like 1, 3, you know these. And these are for squares, you know squares. They make a square. These ones make a triangle. Maybe that's the solution. Actually, it could be 3. So 3 plus 4 equals 7. Let's put the EG up here. I think I can turn this into a quadratic form question, but it's a quadratic form with 3 variables for the 3 shapes. So I don't know how to solve those, technically speaking. Yes. Wait, what's 2020? 2025 is good because it's a square. I've no idea how hard this is. I think it might be very hard. Or I've been using facts from Hatcher. Oh, which, surprise. I can do this as a sort of surprise, but I have treated myself to a physical copy of Hatcher, which also means I think that Hatcher has got some money from me at last after using Hatcher's free PDF for so long. I now have a physical version of the classification of quadratic forms, which might be helpful. It might encourage me to actually look at the material in between streams. Who knows? Maybe I will get good at this. The Discord is unofficial. I have kind of mixed feelings about Discord sometimes. I'm not always on there. I'm not certain it's a good idea. Well, what's that emote? That's a lovely emote. Brain M2, yay. Okay, I'm gonna work out. Right, good. Nice to see you all. Have a good rest of your weekend. Week, I suppose. I think I'm live next week. If I'm live next week, might talk about that. Might talk about the binomial coefficients thing. It's a chance that I managed to get the thing to work. Of course, you got the really hard book, the algebraic topology one. My goodness. It is extremely warm here, so I'm going to sign off now and find something cold. Right. Take care, everyone. Enjoy your maths. See you next week. Bye. I'm ending the stream.